Okay, if we have a look at number 20, let's put it up on the board. You had what was the voltage of the battery? 24 volts. Okay, then a resistor, unknown resistance, R. Two resistors down here, V2 and V3 over them. Another resistance R, let's call this R1 to keep it simple, R2. And this resistance here is 1 ohm. Okay, there's also an 8 volt reading over V4. Seven ohm resistor on the side, V5. Right, is there anything I've left out? Sorry? Voltmeter V1. Thank you. Sorry? Is that it? Okay, right. Who'd like to do this one? Jock? Okay, Richard, you answered the other day. Richard? No, just tell me what's what. Just reason. Otherwise it takes too long. The bottom two, yes? Yes. Why do you say that that is 2 volts? 8 volts over those 2, that's 6, therefore that must be 2, all happy. Okay, give me another thing that you're reasoning with. So this is 3 times more voltage than that, so that must have 3 times more resistance. All happy so far? Okay, carry on. V5 in the same ratio, yes. 1. Okay, well I would just have said this is 7 times more resistance than that. Okay, so you'll get 7 times more voltage. Or you'll need 7 times more energy. You all agree? 14 volts, okay. Right, R1. You go to, how did you get that it's 2 volts? Okay, so you got 14 and 8, that's 22. So that would be 2 volts over there, right, okay. 1 ohm, how did you get that it's 2 volts is 1 ohm? 2 volts, 1 ohm. 1 ohm gets, every 1 ohm gets 2 volts, so that must be, right, who got all of that right? Pauline, where did you go wrong? Okay, understand that where the 14 comes from. Okay, and obviously a whole lot of other things went wrong after that. Okay, so that is, and as we mentioned the other day, all of these resistors are in series. There are no parallel resistors. You've got the voltmeters are in parallel, yes, but they don't count. Now, voltmeters, do they have a high resistance or a low resistance? Low resistance, you all agree. Okay, so the electricity flows out of there. Where does it go to when it gets to that point? Through the resistor or through the voltmeter? 99.99999% must go through the resistor. That's where you want the electricity to go through. That resistor may be a light bulb. You don't want the electricity not going through the light bulb. You want the light bulb to work. So what must the resistance of a voltmeter be? Extremely high. What is the voltage of what is the resistance of an ammeter? Extremely low. Why is an ammeter extremely low? That's connected in series, so the electricity's got to flow through it. You don't want to slow the electricity down, so you make it low. But if you make that one with a low resistance, where will the electricity go when it gets to that point? It's going to all go through there. So this must have an extremely high. So you need to remember that voltmeters are connected in parallel and they have an extremely high resistance. Ammeters are connected in series and they have an extremely low resistance. Remember that, please. These resistors are all in series, and what do series resistors do to the voltage? No, they don't increase the voltage. The voltage is 24 volts. What do they do to the voltage between themselves? They split it up. We said resistors in series are? You wrote it down the page before. Go and have a look. Voltage dividers. Somewhere you wrote it down. Okay, resistors in series are voltage dividers. Third of the way down, page 12. There it is, you've written it down. Right, now we're going to have a look at resistors in parallel. Same type of reasoning. Yes? Page 9.5, I know. My apologies for not being here yesterday. I was at a last moment told that I had to attend a meeting for principals that was meant to go on until 4:30, from 9 to 4:30. In the end, I got back in time for your extra lesson yesterday, but you had already been told that that was called off, so I didn't persist with that. So I apologize. It wasn't part of my planning, but that's the way it goes. Okay, let's have a look at page 13. Where's my cursor? Okay, if we have a look at page 13, we're now dealing with resistors in parallel. So let's have a look at what we've got up here on the screen. In all of the previous examples, the resistors have been connected in series. This has meant that while the voltage has been divided up, the current has been constant throughout the circuit. Let's stop and let's just see what we mean by that. Where was the current the strongest here? It was the same everywhere. Remember, we've drummed that into you people. We've said in a series circuit, the current is the same everywhere. Okay, remember that. Okay, the current has been constant throughout the circuit. Let's now look at resistors in parallel. For example, you've got a situation of two resistors in parallel there. Now, which resistor is more difficult to travel through, the 4 ohm or the 2 ohm? 4 ohm. More difficult to travel through the 4 ohm. How many times more difficult? Twice. Now, how much current have you got coming down that branch there? 3 amps. That 3 amps is now going to split up. You can't have 3 amps going there and 3 amps going there. It's got to split up. Which branch do you think will get most of the 3 amps? How many times more will that branch get? Twice as much compared to that. Who can divide 3 amps up so that that gets twice as much current as the 4 ohm branch? Mika? You're going to give 2 amps there and 1 amp there. Yes. Okay. So current will rather flow through the easier route. Okay. The 4 ohm resistor is twice as difficult as the 2 ohm resistor, right? Therefore, the 2 ohm resistor will receive twice as much current. The easier the resistance, the more current it gets. Okay? Therefore, if you take your 3 amps, I'm now just stretching this out. Okay, here your 3 amps approaching. There's your 4 ohms, there's your 2 ohms. That one will get how many amps did we say, Nikita? 1 amp, and this would get? Now, what do you notice about that plus that? They add up to your 3 amps. Now, over here, what did you know about your current everywhere? It was the same. Your current wasn't splitting. But what did we learn about that voltage plus that voltage? So your voltage all added up. Yeah, your voltage, we'll look at that in a moment, but your currents now all add up. Let's just go back to that. What did we say the current there was going to be? There, 1 amp, there, 2 amps. What does that add up to? The original 3 amps. Okay, so resistors in parallel are what dividers? They divide the current up. They are current dividers. Resistors in series are voltage dividers. Send these around, please. Right, I'll hand out page 14 now. Of page 13. No, I don't have an extra page 13. I will have to get it to you. Who's it for? Okay, right, let's listen up here. Let's have a look at this thing that we got here on the board. Coming in over here, you've got 4 amps of electricity. The current is 4 amps. Okay, what is going to happen to that 4 amps when it gets to that point there, which I'm marking with a green dot? It's going to split. Do you agree you've got a 2 ohm branch and a 6 ohm branch? Which branch has got the higher resistor? 6 ohm. Which branch is the easier? 2 ohms. How many times easier is 2 ohms than 6 ohms? 3 times easier. So it must get how many times more current? 3. Now we're dividing 4 up. This one must get 3 times more than that, but they must add up to 4. So what is this going to be, Luto? 3 amps. Which you can't see too clearly. Can you see that now? And this will obviously be 1 amp. Let's just double check. First of all, is this 3 times bigger than that, because this is 3 times bigger than that? Okay? Do they add up to 4 amps? What will this reading on A4 be again? It will recombine over here at this point, and we'll take it back to 4 amps. Okay, so the current has been divided up in this case. Right, I'd like you to do, just fill that in there on number 20. Then you can do number 21, please. Has everyone finished number 21? Anyone not finished? Right, let's have a look at number 21. How much current have you got coming into that setup? 5 amps. What are your two resistors? 6 and 4. Which one's got to get more current? 4 ohms, yes, okay. How many times more? 1.5 times more. Can anyone divide up 5 amps so that this 4 ohm branch gets 1.5 times what the top branch gets? What is A3 going to be reading? 3. And A2, 2 amps. So is 3 amps 1.5 times 2 amps? If we compare 3 amps, so we said we had 5 amps coming along, and it's going to break up into 3 amps and 2 amps. I'm not too sure which one is top and bottom. Doesn't matter. Okay? Is this 1.5 times that? If I said 2 times 1.5, would it give me 3? Yes. So that is 1.5 times more current. This would be the what ohms? 4 ohms. This would be the 6 ohms. Right. Okay. Do the 2 amps and 3 amps add up back to the 5 amps? Yes. Okay, do number 22, please. Okay, let's have a look at number 22. Oh, okay. What's the case here? You need to find the resistance and you need to find the ammeter reading. Any suggestion who's going to take us through that? I'm getting the same people volunteering all the time. Christopher? What will the reading on A3 be? 4. How did you get that? You started off with 6 amps over there. That's 2, so that must be 4 amps. Okay, right. Yes. R must be 14. That must be 4. 4 amps, 14 ohms. All happy? Who's not sure of that? Okay. Do number 23. What time does this lesson end? 5:02. Okay, let's have a look at number 23. Still busy, okay. Okay, let's go to number 23. Who'd like to do this one, please? Someone who hasn't done one before? Right, or where to? That will be 4.5, okay. The difference between, or the how many times 4 point bigger? Okay, so it's 9 times bigger. So 4.5 amps there is 9 times bigger than 0.5, yes. 63 amperes, ohms, that is correct. No, think about it. Which has got the bigger resistance, 2 or 6? Which one gets more current? The one with the lesser resistance gets the bigger. Understand why we're saying that? It works just back to front. Okay, understand where it comes from? Good. Now, that's nice and easy because you can more or less work it out. What if I'd given you resistors of 7.62 and 11.71 and currents like 13.63? What are you going to do now? Formula, yes, you're going to need a bit of a formula. So let's just have a look. Over here, what did we say with these two resistors? Which one was the bigger resistor? 6, how many times bigger? 3, so that one gets 3 times more current. The bigger resistance gets 3 times less current. Okay, is there a way that we could work it out if those numbers were not nice and easy numbers? Let's work with the easy numbers first, then we can always do one with tough numbers. What you do is you say, right, if I want to work out how much is coming through here, I take my main current, 4 amps, okay, and I put it over 1. You all happy with what I'm doing? Watch what I'm doing because you've got to know how to do it. You take your main current because we try to divide the current up. Now, this branch here is going to get that much. 2, okay, over, add the 2 together, 2 plus 6. 2 plus 6 is 8. 4 goes into 4 once, 4 goes into 8 twice, gives me, there we are. Okay, who can tell me how I'd work the top 3 amps out? I'd say what current? 4 amps over 1 times the other resistor over the sum of the two resistors, 2 plus 6, and that's now going to give me 1, 2, it's going to give me 3 amps. All happy with that? Let's just turn back to your previous page and right down at the bottom of page 13, you'll see the way of doing it there. Okay? Let's just have a look at those 2 examples. You all paying attention here on the screen? How much current is coming into that split? 3 amps. 4 ohms there, 2 ohms there. So if I want to find how much goes through A2, I'm going to take my 3 amps over 1. You all agree with that? And which resistor am I going to put on top? The 4 or the 2? I put the 2, the wrong one. Because if I'm trying to find out how much is flowing through there, I put that resistor on top. Okay? 2 over 4 plus 2, and it gives me 1 amp. Right. If I'm trying to find out how much flows through there, I take my 3 amps over 1. I put the wrong resistor, 4 ohms over 4 plus 2, gives me 2 amps. Highlight that, make sure you can do it. Gets a little bit more complicated. Okay, I don't want to go into that now. You would have to, if you had 3 resistors, you would say 1 over the sum of the other. You've got to actually work out what the other two are worth, and then say that plus the sum of that. It becomes a lot more tricky. Okay, but let's have a look at this. Who wants to choose? Oopsie. Yeah, we'll do that. A2, A3, A1. Let's make this 6,5 amperes. Let's make this 2,5 ohms and 5,5 ohms. Okay, work that one out. I want to know what the readings on A3 and A2 are going to be. Just at this stage, I'm interested in how you do it. Do you know the method? Okay, let's have a look at this. Who would like to tell me how to do it? Dylan?
Well, for
A2? 5,5 over? Good. What does that actually come out to? Okay. Without doing the whole calculation again, could I work out what this current is? How would I do that, Nikita? Minus 4.47 would give you the answer. But let's do it. Nikita, tell me how to do it. 2,5. 2, equals 2,03 amps. As a double check, does that plus that add up to 6.5? Yes. Good. All happy? Fantastic. Right, so we're now finished with page 13. We went back to it. I want you now just to pay attention here on the board. If I said to you, you had 6 amps, okay, you had 6 amps coming in there, 2 ohms, 1 ohm. What are your 2 ammeter readings going to be, please? Armella. Which one will get more? How many times more? 2 times more. So divide 6 up so that this gets 2 times more than that. Could it be 3 and 3? Is it? Is that 2 times more than that? No. So 3 and 3 doesn't work. Which one? 4. That one, 4 amps. This code pen is dead. And 2 amps. Does that add up to 6? Okay, good. Now, what would happen if I put a voltmeter over here? Let's put the voltmeter inside. We'll call that V2. And I'd have put another voltmeter there. We'll call that V3. Did anyone tell me what those voltmeter readings would be? Both before. Well, what's your reading for voltage? Or your formula, V equals I times R. What is the current that's flowing in that point, out that point? You've just worked it out, 4 amps. What is the resistance between that point and that point? And that gives you 4 volts. Oh, okay, right. So you got it. Let's have a look. Let's calculate V3. So that's V2, eh? V3 is also I times R, you agree? What is the current that's flowing in there and out there? And Miller just worked out, it's 2. What's the resistance between there and there? 2 gives us 4 volts. Okay. Is it coincidence? You think not. Okay, let's put another voltmeter in here and let's check. If it happens 3 times, maybe it can't be coincidence. Let's put a voltmeter there, which we will call voltmeter number 1. We call that voltmeter 1. Okay, so that's a voltmeter that's over the whole lot combined. So this voltmeter was just over the 1 ohm. That one was just over the 2 ohm. This one is over both. What's your formula for voltage? V1 equals I times R. Can anyone tell me what is the current flowing in there and out there? Okay. What is the resistance between that point and that point? 2 over 3 ohms. Well, we're going to have to do the calculation. 1 over R parallel is 1 over 2 plus 1 over 1. You agree? Common denominator 2. 1 plus 2 gives us 3 over 2. 1 over R is 3 over 2. Therefore, R is 2 over 3 ohms. So let's put there 2 over 3. What is 6 times 2 over 3? What do you notice? The voltage remains the same. So where you've got resistors in, what are they? Parallel. Whether you measure the voltage over one of the resistors, or over the other one of the resistors, or over both of the resistors, or even if I put a voltmeter in like this, V5, or whatever you want to call it, like that, it would still read 4 volts, provided the voltmeter is over a resistor. If I had to just put a voltmeter in like that, would that be over a resistor? No. Then that would read 0. Okay. But any resistor that's over a resistor in a parallel combination, the reading will be the same. There are a couple of exceptions which we'll look at in a moment. Yes? Which one? Read the battery strength. No, it's not reading the battery strength. Put it over ammeter 1. You'd need to put it, this one, V1, if the battery is down here. So V1 is over the battery, but this isn't. Okay. Because you've got to say between its terminals is there, you can't take this wire that way and this one that way. You'd have to bring back, and it's not going to work. Okay? You're going to have to move it over other appliances. Yeah. So, what did we say? Voltage over what type of resistors? In parallel will always be the same. What happened with the voltage over resistors in series? What did they do? Did they have the same reading? What did they do? They divided the voltage up amongst them. They all had different voltages. What was the same with a parallel circuit? What stayed the same everywhere? What? The current stayed the same. So in a parallel circuit, the current is the same everywhere, but the voltage is different. In a series circuit. Okay, let's go back to it. Turn back in your notes to page 12. Okay, you're all on page 12. Examples 15 down to 20. How were those things connected? Series. What was the same everywhere in each of those circuits? Current. What got divided up? Voltage. We turn to page 14. Let's have a look at that example number 24. Okay, that's the example which I've got on the board. Did the current stay the same? No. Your 6 amps became 2 amps at the top, 4 amps at the bottom. It split up, it divided up. Did your voltage stay the same? Yes. Okay. So, I'd like you to do number 24 now, please. Right, that will be your homework for tomorrow, to do number 24. When I see you tomorrow, we'll mark that, and we'll start looking at some more complicated circuit diagrams now. Okay? Right, thank you.